I would like to talk about some variant of domination in graphs. It will be domination called super domination. But first, I'd like to present some history of dominate and definitions of domination problems in graphs. Historically, this kind of problems came from chess. In 1950s, some chess players were interested in the minimum number of queens, such that every square on the classical chessboard 8 by 8 either contains a queen or is attacked by a queen. Recall that if we have a queen, for example, this queen, then this queen can move any number of squares vertically, horizontally, or diagonally in both sides. Here we have the solution of the problem. We can see that 5 queen is enough to solve the problem. And this kind of problems, it was beginning of thinking of domination in graphs, because with the chessboard, we can associate a graph Qn. It was difficult for me to work with traditional chessboard, what means the graph Q8. So I decided to show you the smaller chessboard, 3 by 3, and the vertices of the graph correspond to the field of the chessboard. So if we have this small chessboard with 9 small squares, then a corresponding graph will have 9 vertices. And the edge between the vertices we have when the corresponding fields are reachable by the queen. So, for example, if we put a queen, if we would put a queen here in the number 5, then the small squares which we can reach from this field is 1, 9, 3, 7, 2, 8, 4, and 6. So in the corresponding graph, if we have a vertex number 5, this vertex will have neighbors 2, 4, 6, 8, 7, 3, 1, and 9. Here we put a queen here in this first small square, and the other queen here in the square numbered 8. And we can easily see that these 2 queens dominate this small chessboard. What means that also these 2 black vertices in corresponding graph also dominate all the graph, in this sense that every vertex in this graph is either a black vertex or has a neighbor in this set of black vertices. So here we have a dominating set of cardinality 2. It's not a minimum dominating set, because it's possible to find a smaller dominating set here. For example, if we put queen here in this vertex 5, then this vertex can dominate all this chessboard, and also the vertex number 5 can dominate all the graph. But here we have just an example of a dominating set of cardinality 2. I would like also to show you some example of application of a domination problem. We can consider something like a computer network, and the mathematical model for this network can be a graph, when the computers are the vertices of the graph and the edges, the links between them represent the edges. Here we have a picture. And imagine that we want to monitor the functions of each of the computers by a small number of computers in such a way that every of these computers can control the neighbors. In graph theory, we call these controllers a dominating set. Here on the picture, we would like that these big computers dominate all these networks. And it is almost done. Every computer except of this one is dominated by one of these bigger computers. And we can notice that if we exchange the rules between this and this computer, then we obtain the dominating set of cardinality form here. And we can ask the questions, for example, what is the minimum number of computers required to completely control the communication network, and how we can find such a minimum dominating set. And I must also mention that we have lots of kinds of domination. We have varieties of domination. Now there exists more than 100 variations of domination. And what does it mean, variation of domination? In these variations, we require from a set of vertices to be a dominating set, but also to have some additional property. So the set is dominating and also has some additional property in this sense that we can give some conditions on the dominating set. For example, subgraph induced by this set can be connected or independent, and so on and so on. Or we can put some conditions on the complement of this set. And in this way, we can obtain some variation of this classical domination problems. The first and the most famous book when these problems of domination were described, something like a Bible of Domination, is a book of Teresa Haynes, Stephen Hedet-Niemi, and Peter Slater, entitled Fundamentals of Domination in Graphs. Now I would like to present some more formal definition of dominating set. If you have a set of vertices, then we call this set dominating if every vertex outside of this set has at least one neighbor in the set. So here on this picture, the set of red vertices is a dominating set because every black vertex from the complement of the set has a neighbor in this set of red vertices. And we are usually interested in the minimum number of vertices in such a set. So we are interested in the minimum such sets. And the minimum cardinality among all dominating sets in G is a domination number of G denoted by gamma of G. And here we have some examples. In the first graph, domination number of this graph is equal 1, and this central red vertex of this star dominate all of the graph, the whole graph. And of course, this is a minimum dominating set because it's not possible to find a dominating set of cardinality less than 1. Here in this graph, it's also quite easy to observe that no single vertex can dominate of this graph, but two vertices, it is enough. So these two red vertices dominate this graph because every white vertex has the red vertex as a neighbor. So here we have an example of dominating set of cardinality 2. Here in this third graph, we have example of graphs with domination number equal 3. And it's quite easy to verify that these 3 red vertices form a minimum dominating set of this graph. I said at the beginning that I would like to talk about some variant of domination called superdomination. But to define the superdomination, I need the idea of the private neighborhood. Here is a definition, but it looks not very friendly, so it's better to explain this definition showing the example. Here we have a graph, and we have a set of red vertices x. And we can say that the vertex A, this black vertex A, is a neighbor of red vertex X. But also we can say that it's private neighbor, because this vertex A has the only one red neighbor. X is its only one red neighbor. So we can say that A is a private neighbor of X with respect to the set X. In the case of this vertex C, we can say that C is a neighbor of a vertex X, but it's not a private neighbor of X, because C is also a neighbor of the other red vertex Y. So C is a neighbor of X with respect to X, but not a private neighbor. So this is the idea of the private neighborhood. And if you want to define a superdominating set, then we can do it in the following way. If we have a set D, which is a set of subset of the set of all vertices, then we call the set a superdominating if it's, of course, dominating. But for every vertex belonging to the complement of the set, there exists a vertex belonging to the set such that this vertex U is the only neighbor of vertex V with respect to V minus D. So here we have this situation where this vertex U is an external private neighbor of a vertex V with respect to the set V minus D. Here we have a quite simple example. The set of vertices D, the set of these red vertices, is a superdominating set because, of course, it's a dominating set. Every black vertex has a red vertex as a neighbor. So this condition of being dominating is fulfilled. But also it's a superdominating set because, for example, this vertex U, it's a neighbor, has a private red neighbor, such that this neighbor is not a neighbor of any other black vertex except of U. So here this vertex U has this vertex V as a private neighbor, and this second vertex, black vertex, has this vertex private neighbor, this red vertex as a private neighbor. And here also we are interested in the minimum such sets. So the minimum cardinality among all superdominating sets in G is the super domination number of G, denoted by gamma indexed SP of G. Here we have the same graphs as before, but now these red vertices form not only a dominating set, but super dominating set. We can see here in this first example that this white vertex has a red vertex as a neighbor, And this neighbor of a white vertex has not any other white vertex as a neighbor. Here, in the second example, we have a superdominating set of cardinality 3. This white vertex has this red vertex as a private neighbor. This white vertex has this red vertex as a private neighbor. And to keep this property that the set is superdominating, it was necessary also to put to the set this vertex. Here we have also example of a superdominating set. It's not so difficult to verify that this is a minimum superdominating set. And at the first look of these examples, we can see that in general we really need quite a lot of vertices in a graph to form this superdominating set, even if it's minimum. Here, I decided to put some example just to understand better the idea of superdominating set. We can consider a superdominating set D here as a set of women and the complement of the set, so the set V minus D, as a set of men. An edge between two vertices belonging to the set D denotes the relation between two women, that two women know themselves. But this condition of being a superdominating set is that each man from V minus D, for example, this man, has a special woman, V, and this woman is his wife, and this man does not want that his wife talk with the other man because, for example, he is jealous. So this kind of edges are forbidden. The other example, in the same way, we can consider a superdominating set D as a set of professors, and the complement of the set as the set of PhD students. And every student from V minus D has the supervisor, has the professor who is his supervisor. And every professor must have at most one PhD student. More than one is not allowed. This relation is not allowed, just to work with the student more efficiently. And in 2015 appeared the first work, the first publication about superdomination in graphs. We defined this kind of domination. Me with my friend Rita from Mexico and with two men from India, we published the first paper about superdominating sets. And in this paper, we put these basic properties. For example, that the superdomination number of a graph is equal to 1 if and only if G is a single vertex, or the graph K2. Superdomination number is equal to n if and only if G is an empty graph. Empty graph is just a graph which has only vertices without edges. And here is this property that I mentioned, showing you some examples of superdominating sets, of minimum superdominating sets, that we require we always need quite a lot of vertices to form this set. And we proved that at least half of vertices we always need to form this super dominating set, even if it's minimum. And we put also some relation between super domination number of a graph and classical domination number. Of course, because of this property that super domination number is equal to n if and only if G is an empty graph, if we have a connected graph, then super domination number is always less or equal n minus 1. And at the beginning, we were almost sure that this equality is that super domination number is equal n minus 1 is impossible. But in the next our paper, 4 years later, we managed to define the family of all graphs for which this equality can happen. First, this is a work also common with Magda Detlav from Poland, Rita Zuazua from Mexico, and Juan Alberto Rodriguez Velasquez from Spain. And we were thinking about in this work, we were thinking about the problems of super domination number of lexicographic product of graphs. But first, we need some results about equality, super domination number equal to n minus 1. And first we notice that if super domination number of G is equal n minus 1, then G is P free and C free. And the other property that if super domination number is equal n minus 1, then G contains at least one universal vertex. Universal vertex is a vertex which is a neighbor of every other vertex of a graph. Here is a definition of the family of graphs with the equality, but again, this definition looks not very friendly, so I decide to just to show some examples of graphs belonging to this family. It's quite easy to see that in this all these examples we have not induced P4 and we have not induced C4, and also every of these examples contains a universal vertex, so a vertex which is a neighbor of every other vertex of the graph. And we managed to prove that super domination number of graph G is equal n minus 1 if and only if G belongs to this family F. And we considered also the problem of super domination in lexicographic products of graphs. And again, here it's a formal definition of this lexicographic product. But I decided to show you this definition by example. If we consider a lexicographic product of a graph G and the family of graphs H, then this family H must have the same number of graphs as we have the number of vertices in a graph G. So if we have here a graph G with 6 vertices, then this family H must have 6 graphs. So instead of the vertex, the first vertex of the graph G is U1, we put the first graph from the family H is the graph H1, and the same, for example, in this relation between U2 and H2, and because we have edge between two vertices U1 and U2, then we put edges between every vertex of H1 and every vertex of H2. And this is the idea of creating of a lexicographic product of a graph G and the family H. Of course, it is possible the situation when the all graphs of this family are the same. Here we have this case. If all graph in the family H is, for example, P3, then we have a lexicographic product here of the G and P3. And here is a picture of this graph. And we managed to obtain some bounds concerning the super domination number in lexicographic product of two graphs in terms of super domination number of graphs G and H. Here is the lower bound with and the graphs with equality are characterized. Here is an example of some upper bound, also in terms of super domination number of graph G and H. And using this equality, using this result, we manage also to obtain the quite nice result that the problem of finding of the super domination number of a graph is in p-hard, what means that in general it's not so easy problem. Of course, sometimes when we have some easy families of graphs, like for example stars of complete graphs, it's not difficult to find a super domination number of this kind of graphs. But in general, if we want to work with any graph, the problem is complicated. And we begin this work with super domination in graphs. And I would like also to mention some other papers about super domination. Not a very long time after our work about lexicographic product, we published, me and my friend from Spain, we published some paper about domination related parameters in rooted products graphs. One of these parameters was super domination number. Then some people also consider connected super domination in graphs, what means that we have some additional property put on the set of vertices. First, the set must be dominating, then super dominating, and also they put this third property that in addition this set must be also connected. And the other people continue the study about this super connected domination in graphs. And also in 2019, some people study domination number of unicyclic graphs. And the last work in 2020, written by Juan Alberto Rodriguez Velázquez and two other persons, entitled just on the superdomination number of graphs. In this work, there are lots of upper and lower bounds for superdomination number in terms of many graph theory parameters. Okay, so thanks a lot for your attention, and this is what I wanted you to talk about this kind of domination.